are back with 278, still in the 6th grade. This week focusing on expressions and equations. This is another lengthy standard that students participate in. So I just want to reiterate, I know I've said it time and time again though, that you have all year to go through all these standards. So although we're going through them pretty quickly and I'm assuming you know some knowledge, it's just to give you an idea again of the types of problems students are going to see, and then further using manipulatives to help them and visual models to make connections. And then here's some other ones as well. Algebraic expressions can represent both a recipe and a quantity, such as the sum of 3 and a number. So the word sum needs to add, and we want to add 3 and some number which we don't know. So since we don't know the number, what we'll do is just classify it as a variable because it can change. We don't know what that number is. Or less than a number. So we're having 4 and a number, but we want 4 that are less than or smaller than that number. So if our number is 10, 4 less than 10 would be 6. So what we're really doing is taking that number and subtracting 4 from it. So it's not always written mathematically as we read it verbally. The difference of 4 and a number. So I want to take 4 and a number and find their difference, which means subtraction. So 4 minus some number. These ones that we just talked about each have 2 terms, a number and a letter of sorts. The product of 5 and a number. So product means to multiply 5 and some number. So you can put it in parentheses or squish them together. This one though has 2 factors. Remember, factors are pieces that we are using when we're multiplying. The sum of 3 and the product of 2 and a number. The sum of 3 and the product of 2 and a number. So I really have 2 different parts here. I'm adding 3 and the product of 2 and a number. So the product of 2 and a number is written 2 times that number, and then I want to take the sum of that with 3. So 3 plus 2 and the number. Find the value of the expression when n is 5. So I'm going to stick where n is. I'm going to replace n with 5. So 3 plus 2 times 5 is 3 plus 10, which is 13. Heather has 4 more than twice as many marbles as Amber. Write an expression for the number of marbles Heather has. So Heather has 4 more than twice as many that Amber has. We don't know how many Amber has, but we do know that she has 4 more than. So twice as many marbles is written as 2x, and then 4 more than whatever she has, we add 4 more to it. So if Amber has 3 marbles, how many marbles does Heather have? So we will replace x with 3. 2 times 3 plus 4 is 6 plus 4, which is 10. So Heather has 10 marbles. Words can be used to write an algebraic expression, and we can find a numeric value for the expression if we know a specific value for the variable in the expression. Match each phrase to the expression described by the phrase. Take a moment to pause the video and see if you can't match them up appropriately. The sum of 2 and a number. So 2 plus n, which is letter D. 2 more than a number. That would be letter E. Whatever our number is, add 2 more. The difference of 4 and a number. That would be letter G. 4 less than a number is letter A. Whatever the number is, we want 4 less than whatever that number is. The product of 2 and the sum of 4 and a number. So the product of 4 and a number, when I look at letter F, is the 4 plus n, but I want to take the product of 2 and that portion. The sum of 2 and the product of 4 and a number. So the sum would be our addition. So when I look at letter H, 2 plus the product of 4 and a number. The product of 4 and the difference of a number and 2. That would be letter B. The product of 4 and the difference of 2 and a number. So it's written differently. Joey has 5 less than 3 times the number of pencils Samantha has. Write an expression for the number of pencils that Joey has. So he has 5 less than whatever Samantha has, and Samantha has 3 times x. How many terms does your expression have, and how many factors are in the first term of your expression? The expression has 2 terms because we're adding or subtracting 2 pieces together. And within that first term, 3x, there are 2 factors. Let's say Samantha has 3 pencils. Use your expression to find the number of pencils Joey has. We will plug in 3 or substitute 3 in for the variable. 3 times 3 is 9. Adding to 5 is 14. So Joey has 14 pencils. How many factors does the expression x plus y minus 3 times x minus y plus 4 have? Well, there's actually 2 pieces being multiplied here, so there are 2 factors in this expression. Each factor, though, has 3 terms in it. How many terms does the expression x plus 2y minus 4 have? Here, I have 3 pieces being added or subtracted, so there are 30 terms in the expression. A chef is getting the kitchen of her new restaurant ready for the restaurant's grand opening. Use your volume expression to decide which container is the best choice for each ingredient. Below, we have some ingredients and the amount that they need, or we have, and then we have some containers. These are right rectangular prisms with a square base. So our volume is base times height. And remember, base is length times width because we have a square. So when I look at my large container, we have 16 times 16, so width times length times height, so 20. This is the same as 16 squared times 20, and 16 squared is 256 times 20, so 5,120 centimeters cubed. The medium will be at 10 times 10 times 20, or 10 squared times 20, which is 100 times 20, so 2,000 centimeters cubed. And then the small one is 8 times 8 times 20, or 8 squared times 20, giving us 64 times 20, so 1,280. Those that can fit into the large container are those that are closest to and over 2,000, so because they won't fit in the medium. So it looks like flour and sugar are both larger than 2,000, but not larger than 5,120. Rice looks like it'll fit in the medium container because it contains exactly 200 centimeters cubed. And then baking powder, salt, and cornstarch all are less than or equal to 1,280 centimeters cubed. So that'd be a good one for them. This rectangular prism has a length that is twice its width. If the width is x centimeters, what is the volume of the prism? So I have the prism labeled for us. So on one side I have x. On the other side we have twice whatever this side is. So we can still use our volume formula of the area of the base times the height. So the area of the base would be 2x times its height, which is 10. This is 2x squared times 10, which is 20x squared centimeters cubed. Write algebraic expressions to represent the number of pencils each student took and the number of pencils the student took altogether. How many pencils were in each pack? How many pencils did each student take? So student A said, I took 1 pack and 5 pencils. Student B said, I took 3 packs and 4 pencils. Student C said, I took 2 packs and 1 pencil. The teacher said, I started with 76 pencils. Let's start with student A. Since we are unsure how many are in each pack, we will call a pack X. So student A took 1 pack and 5 individual pencils. Student B took 3 packs, so 3 X's, and 4 pencils. Student 3 took 2 packs and 1 pencil. So the total pencils that are all together are adding the different expressions, x plus 5 plus 3x plus 4 plus 2x plus 1. Using my properties, I can grab all of the x's and put them together and all of my individual pencils and put them together. I see that 6 packs plus 10 extra pencils is how many we have. So let's see how close we can get to 76 pencils all together. So let's say we start with 5. Do we have 5 packs? So 6 times 5 is 30, plus 10 is 40. Gotta go a little higher. Let's try 10. Let's say we had 10 packs. 6 times 10 plus 10. So 60 plus 10 is 70. Ooh, very close. So let's try 11. 6 times 11 plus 10 would give us 66 plus 10, so 76. We found our pencils, so there are 11 pencils in each pack. Let's go ahead and substitute 11 in for each X so we can determine how many pencils each student has. So 11 plus 5 is 16. 3 times 11 plus 4 gives us 33 plus 4, so 37 pencils. And student C had 2 times 11 plus 1, so 22 plus 1 for 23 pencils. The commutative and associative properties simplify variable expressions for us. Jocelyn, Ashley, and Cammie have some packages of candy and some single pieces of candy from open packets. Jocelyn has 2 whole packages and 8 other pieces. Ashley has 4 packages and 1 other piece, and Cammie has 3 packages and 7 pieces. Write and simplify an expression for the total number of candy pieces the 3 students have. So we don't know how many candies are in each package, so we will label them as X. Jocelyn then has 2 whole packages plus 8 other pieces. Ashley has 4 packages and 1 other piece, and Cammie has 3 other packages and 7 pieces. Altogether then, we have 2x plus 8 plus 4x plus 1 plus 3x plus 7. We can use the associative and commutative properties to rewrite all of the packages of candy together plus the individual pieces. So 2x plus 4x plus 3x gives us 9x, and 8 plus 1 plus 7 is 16. Let's start to see if we can't determine how many packages of candy we have. Let's start with 10. 9 times 10 plus 16 is 90 plus 16, which is 106. Not quite there yet, so let's try 11. 9 times 11 is 99, plus 16 is 115. All right, let's try 12. 9 times 12 plus 16 is 108 plus 16. We found our 124 pieces. So there are 12 pieces in each package. Let's determine how many pieces of candy each of the cousins have. So 2 times 12 is 24, plus 8 is 32. 4 times 12 plus 8 is 48 plus 8, so Ashley has 56 pieces. And Cammie has 3 times 12, or 36 plus 7, so 43 pieces of candy all together. Each day, Mrs. Hall gives her cat 1 container of food and 3 more pieces of food. Write 3 different algebraic expressions to represent the number of pieces of food eaten in 5 days, 10 days, and in 30 days. And explain what the variable represents in each expression. So let's let X be the number of pieces of food in a particular container, because we're not quite sure how much is in a container, but we do know that they give 1 container of food and 3 more individual pieces. So therefore, in one day, if she eats 1 container of food and 3 pieces, we can let X plus 3 represent the number of pieces eaten in one day. For 5 days, we would want to add 5 1 days together. So X plus 3 plus X plus 3 plus X plus 3 plus X plus 3 plus X plus 3, representing each of the 5 days. However, we can combine like terms. We see that we have 5 X's plus 15, since we have 3 plus 3 plus 3 plus 3 plus 3, which is 15. So then we can say that the pieces eaten in 5 days were 5 times x plus 3, so 5 times how much ever they eat in one day. We can represent 10 days by taking 10 times the amount eaten in one day, and 30 days by taking 30 times the amount eaten in one day. We can then distribute to identify how many were eaten on each day. Because we know that each container holds 150 pieces of food, we can use our expression to show which size bag would be the best choice for 5, 10, and 30 days worth of food. So if we know that 150 represents the number of pieces in each bag, we can replace x, which we represented as the number of pieces in each bag, with 150, giving us 5 times 150 plus 3, which is equal to 5 times 153, or 765 pieces. Similarly, we'll take 10 times 153, which is 1,530 pieces, and 30 times 153, which is 4,490. Now we can determine which size bag of food would be the best choice for 5, 10, and 30 days. The best option would be the large bag with 5,000 pieces for 30 days. The medium bag wouldn't have quite enough, so we would need to have the large bag with a little extra left over. The distributive property applies to algebraic expressions in the same way it applies to numeric expressions. 3 students disagree about how to represent the model with an expression. Who is correct? Is it Diego, who says it's 2 times 3x plus 12? Is it Susan, who says 3 times 2x plus 8, or Omar, who says 6 times x plus 4? Let's see here. Diego split the model into 2 equal groups. Each group contains 3 x's and 12 units. So there I've boxed in the 3 x's of 12 units. Susan split the model into 3 equal groups, and each group contained 2 x's and 8 units. So now you can see I've split it into 3 different groups. And Omar split his into 6 equal groups, and each group contains 1 x and 4 units. Therefore, we can say that each of the expressions are equivalent because overall they use the same amount, just represented in different ways to model. Diego wanted to experiment to see what happens if he were to replace each variable with the number 6. So he took 2 times the quantity 3 times 6 plus 12, which is 2 times the quantity of 18 plus 12, which is 2 times 30, which is 60. Let's try that method with Susan, replacing x with 6. So 2 times 6, which is 12, and 12 plus 8 is 20, times 3 is 60. And 6 plus 4 is 10, times 6 is also 60. So we can say that they're also equivalent because they give the same number. Rebecca says that 3 times x plus 5 is equal to 5x plus 3, because when 6 is substituted in place of x, both expressions have the same value. Do you agree with Rebecca? Use a model and calculations. Well, 3 times, let's replace x with 6 here and see what happens. 3 times the quantity of 6 plus 5 is 3 times 11, or 33. Replacing it into the other equation, I'd have 5 times 6, which is 30, plus 3, which is 33. What if we tried a different number to substitute, such as 8? So if I replace an each equivalent one with 8, I end up with 39 and 43. Those don't work, so let's try using a model. On the left, you'll see I have 3 groups of x plus 5. So I have 1 group, 2 group, and 3 group. And on the right, I have 5x plus 3. Notice these are not equivalent because they do not create the same shape, first of all. And second of all, they don't have the same amount of 1 values or x values on the left or the right. That tells us then that different expressions can sometimes have the same value. However, equivalent expressions have the same value regardless of which value is substituted for the variable. When Rebecca evaluates the three expressions below for x equals 4, the value of each expression is 36. Rebecca says that this means the three expressions are equivalent. Do you agree or disagree with Rebecca, and why? So yes, by substituting in 4, they all get 36. But let's look at the visual representation of this to see if they truly are equivalent expressions. So on the left here, I have 4 times the quantity of x plus 5. In the middle here, I have 1, 2, 3, 4, 5, 6x plus 12. And then on the right, I have 2 times the quantity of 2x plus 7 plus 6 more. I can see that although these two x values are the same, this one has 15 1 values, and this one has, let's see here, there's 14, 15, 16, 17, 18, 19, 20. So these are not the same. This one has way more x values, so they are not equivalent in any shape or form. Draw area models to determine which expressions are equivalent. See if you can do this. Okay, so here I have 6 times the quantity of x plus 1. Here I have 2 times the quantity of 3x plus 6. And here I have the quantity 3 times the quantity 2x plus 4. Notice that no matter how I were to recreate this, although they all have 6 x's, they all do not have the same unit. They're not going to make the same shape no matter how I try to manipulate these. But perhaps these might be related. Let's see if I can't move some of these around to see if I can't make it the same shape as the one above. If we can, then I know they are equivalent. And I see that I've got 2 copies, or 2 times the quantity of 3x plus 1, 2, 3, 4, 5, 6. So the middle and the right equations are equivalent to one another. Draw area models to determine which expressions are equivalent. Pause the video, see if you can tackle this one. On the left, I have 3 times the quantity of x plus 4 plus 2x. In the middle, I have the quantity 4 times the quantity of x plus 3 plus x. And on the right, I have the quantity of 5 times x plus 3, but then it asks us to subtract 3. So I need to subtract 3 away. Now I see that the middle and the last are equivalent to one another. And no matter how I manipulate, even if I were to, what if I were to bring it like this? I see then all 3 of them are equivalent to each other. And we can find that out if we were to distribute and algebraically determine that as well. So area models can be used to identify equivalent expressions, and models of equivalent expressions have the same area. As we just found, they have to look identical to one another. Heather, Amber, and Danny are trying to decide if the expressions 4 times x plus 2 and 2 times 2x plus 4 are equivalent. Circle the correct work. Here is Heather's work. She has 4 groups of x plus 2, correct? And she has 2 groups of 2x, 1, 2x plus 4. She states that the expressions are equivalent because both models make perfect rectangles. Well, yes, they make perfect rectangles, but they don't create the same area. They don't create the same area. So although her work is slightly correct, it's not totally correct. Amber says that we have the exact same pictures, that the expressions are equivalent because the models have the same area. Amber, you are correct. They have to have the same area. Now, Danny wrote she has the expressions written, but she doesn't have the correct work. She's got x plus 2 and then 4, so her models are not even correct. The expressions are not equivalent because the models have different areas. That's true, they have different areas, but she did not represent using her algebra tiles correctly. So Danny is incorrect. All right, let's write two expressions that are equivalent to 9x plus 15. I see that 3 is a common factor of both terms because 3 times 3x plus 3 times 5 gives me 3 times 3x plus 5. Let's make sure both expressions are equivalent through substitution. So let's use 10. In the original one, 9 times 10 plus 15 is 90 plus 15, which is 105. Doing the same with our new expression, 3 times 10 plus 5, so 30 plus 5, 35 times 3 is also 105. So again, just because they match doesn't necessarily mean that they're equivalent. Let's use a visual model to see what a factor of 4 would look like. So let's start off with 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 15. So here's 3, 6, 9, 12, 13, 14, 15. Okay, so we need 4 distinct groups here. So I'm going to start cutting these off so that I have 4. Oh my goodness, but this guy ain't going to be able to do anything. So we're going to have him hang out here. And then I'm going to start placing my individuals. Okay, remember we can't put them here, guys, because if I were to start doing that, we're going to overlap and it's not going to be, it's not the same. So we have to kind of put them under here where they create a nice rectangle, even though our X here isn't part of the rectangle. Okay. Oh boy, so I see then that I not only have an X left over, but I have 3 individual units. So when I took 9x plus 15 and I divided it by 4, we have 4 groups of 2x plus 3 plus an extra x plus an extra 3 units. So that would look like this if we were to write it out. So this is an equivalent statement to this guy up here. It seems weird, but it's true. Use the properties of operations to determine which expressions are equivalent to each other. I'll start with the one here on the left. I know then that we'll have 3 times 2x plus 3 times 6. That will give me 6x plus 18. All right, so let's move over to the next one. We will then have 4 times x plus 4 times 5 plus the x. This will give me 4x plus 20 plus x. I can group all of my x's together, giving us 5x plus 20. So right off the bat, the first two are not equivalent to each other. What about the third one here? I know that this will be 4 times x plus 4 times 3 plus the quantity 2 times x plus 2 times 3. This will give me 4x plus 12 plus 2x plus 6. Using our properties of addition, we can rearrange these so that we have 4x plus 2x plus 12 plus 6. So altogether we have 6x's and plus 18. So the first and the last expressions are equivalent to one another. Paige and Diego are having a debate about the following problem. If 3m equals 12, what is 5m? Paige thinks 5m is 14 because if I were to take 3 plus 2, I would get 5. So therefore, 12 plus 2 is 14. Boom, done. Diego thinks that 5m should be 20 because 5m is the same as m plus m plus m plus m plus m. Let's see what they're thinking about. Let's use a tape diagram to show who is correct. So we have 3m has to be the same amount as 12. Well, if I take 12 and divide it by 3, each m represents 4 units. So then what about 5m? Well, if each m is worth 4, we'll put 5 4s there. So 5 times 4 is 20. You can use substitution to determine if a given value is the solution of an equation. The solution of an equation is the set of values that makes the equation true. Mr. Williams is throwing his math class a pizza party. If he has 20 students and wants to spend no more than $65, use the table to decide how much of each item he should buy. Let's suppose that Mr. Williams buys 5 pizzas because the pizza serves 4 people. 5 pizzas times 4 people is 20 students, which is how many we have. 3 liters of juice and 5 boxes of cookies. The total cost then would be how much pizza plus the cost of juice plus the cookies. So if we're buying 5 pizzas and each pizza costs $8, we will have 8 times 5 plus the juice, which is $1.99 times 3 of them, plus $4.50 times 5 boxes. 40 plus $5.97 plus $22.50 gives us $68.47. Oh dear. Mr. Williams is over budget. What can he change so that he does not spend over $65? Well, if I take a look at the cookies, there are 5 cookies in each box. We would only need 4 boxes, not 5. Since 5 times 5 is 25 cookies, he would end up with 5 more. Let's do the same equation, except this time, let's use 4 boxes of cookies instead of 5. That would give me 40 plus $5.97 plus 18, which is certainly now less than $65. We can substitute values and evaluate expressions to make decisions and solve problems. The solution of an equation is the set of values that makes the equation true. Mr. Williams is now helping throw a pizza party for the entire 6th grade class on the last day of school. There are 200 students. How much will it cost to buy enough pizza? So notice that the cost is the same and each pizza still serves 4 people. So each pizza serves 4 people. 1 pizza for 4 people. If we have 200 people, how many pizzas will we need? Well, I know that 4 times 50 is 200. So 1 times 50 is 50. We need 50 pizzas. So the total cost would be 50 pizzas times $8 per pizza for $400. If equations are equivalent to each other, the value of the variable in each equation is also the same. So is 18 and 5/10 plus r equal to 26 and 5/10 equivalent to 6x minus 42? So I have a number line here. Let's represent from 0 to about there to be 18.5. And then I want to add a little bit more. We're not quite sure, but we need to add some to get to 26.5. So we can identify what that missing piece is by taking 26 and 5/10 minus 18 and 5/10. So the distance we must travel is 8. Using a tape diagram, 6 times how many is 42. So I'm taking 42 and splitting it into 6 groups. How many are in each group? So 42 divided by 6 is 7. These equations are not equivalent because the value of the variable is not the same. Let's see if 24 minus m is 8 5/10, equivalent to 2x equals 31. Again, I have a number line here. We'll start at 24. I'm subtracting an amount we're not quite sure of to get to 8.5. Well, I know then that 24 minus 8.5 will give us that extra distance. And that would be 15 5/10. Let's look at 2x equals to 31 using a tape diagram. 2 pieces of what gives me 31? So if I divide 31 into 2 different pieces, each piece would have to be 15 5/10. These equations are equivalent because the value of the variable is the same. Because equations show a relationship between expressions, we can use the relational meaning of the equation sign, equal sign, to find a missing value in an equation. Let's start with b divided by 8 is equal to 4. So we're not quite sure what b is, but when we partition it into 8 sections, each section has to be worth 4 units. Well, then I can take 4 times my 8 sections so that I know that b is equal to 32. Since multiplication is used to undo division, multiplication is the inverse of division. G plus 16 is 57. So what plus 16 gives us 57? Well, we can take 57, subtract 16, and that will give us our extra space. So therefore, G must be 41. Since subtraction is used to undo addition, subtraction is the inverse of addition. H minus 21 5/10 equals 13 5/10. So that dotted line represents the subtraction piece. Starting from the whole piece, we're going to take away the 21 5/10. We can add those 2 pieces together such that h is equal to 35. So since addition is used to undo subtraction, addition is the inverse of subtraction. So addition has the inverse of subtraction, and subtraction has the inverse of addition. 5x is 115. 5 copies of what gives us 115? So 115 divided into 5 groups is how many? That must be 23. Since division is used to undo multiplication, division is the inverse of multiplication. Just like adding and subtracting are inverses of each other, the same is true with multiplication and division. Inequalities show a relationship between expressions. We can write the inequalities using the symbols less than, greater than, less than or equal to, or greater than or equal to. 2 bunnies are less than 5 bunnies. So 2 is less than 5. However, 2 less than 5 is actually a subtraction problem. So 5 subtract 2. There is fewer than 3 is fewer than A. So 3 is less than A. Versus the wording 3 fewer than A would be A minus 3. W was more than negative 10. So W is greater than negative 10. Versus W more than negative 10 would be negative 10 plus W. 89 is larger than 87. So 89 is greater than 87. 89 larger than 87 would be 87 plus 89. Max loves his job. His fastest speed is almost, this should say jog, not job, jog. There we go. His fastest speed is almost 6 miles per hour. Well, he's not quite there and he's not over it, so his speed has to be 6 has to be less than his speed. Today's temperature is 10 degrees less than yesterday's temperature. 10 degrees is less than yesterday's high. All right, take a moment to pause the video and go through the following statements to determine which of the 5 can be represented by the inequality x is greater than 7. Jack's cat weighs more than 7 pounds. This statement is true. 7 less than a number. 7 less than a number would be represented by n minus 7. The temperature increased by 7 degrees. That would be represented by t plus 7 or some variable plus 7. Ashley's broad jump exceeded 7 feet. So we're not quite sure how much, but we just know that it is greater than 7. The value of a number substituted for x is larger than 7. So 1, 4, and 5 are all equivalent to x is greater than 7. Solutions of inequalities can be represented on number lines. The words, symbols, and context used in the inequality determine the endpoint and the direction of the ray. A class must raise at least $250 to go on a field trip. They have already raised $75. Write an inequality that represents how much money they have left to raise and graph it on a number line. Our hint here is the word at least. So M plus 75, so the money they have plus the $75 they've already raised has to be greater than or equal to $250. Using addition inverse, we would subtract 75 from both sides such that the money we need needs to be greater than or equal to $175. Notice on our number line at 175, our dot is enclosed or it's circled and it's filled in because it's greater than or equal to. So anytime we have the equal to piece of our inequality, it needs to be a closed dot. Then we need to determine which way our arrow needs to go. I need values that are bigger than 175. So our arrow needs to go to the right-hand side. There are fewer than 200 days until Kevin's birthday. Our hint here is fewer than. So letting x represent Kevin's birthday, his birthday is less than 200 days. On our number line here, notice that 200 is an open circle because it does not have the equal to portion underneath the inequality. We need numbers that are smaller than 200, which means our arrow needs to point to the left-hand side. The words and symbols used in the inequality determine the endpoint and the direction of the ray. Inequalities have many solutions, and those solutions can be represented on a number line. Pete's Pizza and Pasta Shop makes more than 4 pizzas an hour. Which graph represents the number of pizzas that can be made in 3 hours? Pause the video, make your selection. Since they can make more than or greater than 4 pizzas in 1 hour, in 3 hours they can do 3 times as much. So they can do 12 pizzas in 3 hours, but we want more than, so numbers that are greater than, which is why the arrow moves to the right. We can represent the relationship between 2 quantities with an equation, and we also can represent the same relationship using a graph. Look at the perimeter of a square and taking a look at its equation. The perimeter, knowing a square that all 4 sides are equal, a square with 1 would be 4 times 1, or 1 plus 1 plus 1 plus 1. So 4. A square with a 2-unit piece on one side would be 4 times 2, so 8. We then can generalize that it doesn't matter what the length of one of our sides is. When we multiply it by 4, that will give us the perimeter. So the perimeter is 4 times s. Looking at the perimeter of the square here, let's fill in the blanks so that we can graph our points. So if I plug in 1 for s, 4 times 1 is 4. If we plug in 2 for s, 4 times 2 is 8. We plug in 4, 4 times 4 is 16. 4 times 7 is 28. 4 times 11 is 44. We then can go ahead and fill in the points on our line. Plotting the points, you can see that as our side gets larger, thus does the perimeter get larger as well. Try this one, y equals 5x. Pause the video, fill in the blanks, and graph. Notice that we're counting by 5s, or they're all divisible by 5 here. Further, I didn't label my graph, but maybe you did. I labeled down below here by 1s, but I skip counted by 5 all the way up. So this represents 5, 10, 15, 30, and 45. Go ahead and try this one. Y equals 1/3 of x. Fill in the blanks and graph our result. Here we have a few fractions as we multiply, but then they start to become whole numbers, which is okay. Notice that everything that we have done thus far has been a nice straight line. Even though it's a little early in 6th grade, we are building relationships with linear lines. The relationship between two quantities that change together can be shown with an equation in a graph using variables to represent two quantities. Let's fill in the table. We have Indian rupees and US dollars. So we have some Indian rupees and US dollars together with missing pieces. So let's start with that top row. I have 448 rupees. How many US dollars is that? Well, what we can do is divide by 7 to get 1 US dollar by itself. Therefore, if we did 448 divided by 7, 64 rupees would equal 1 US dollar. So if I have 20 US dollars, multiply that by 64, we get 1,280 rupees. Similarly, to go backwards, I know that if I have 1,600 rupees and I were to divide that by 64, we would get 25 US dollars. Relationships between variables can be used to find missing values in a data set. Write an equation that coincides with the data provided. So when I look at the points on the plane here, the number of square feet is along the bottom, the cost of the deck is along the left. The point, if I have 120 square feet, that cost is equal to $2,160. Well, how do I go from that to 1 square foot? What would the cost be? So I divide them by 120, and in both cases, we get the same cost per square foot. So then we can use that information to fill in our table. So this shows us that 1 square foot costs $18. So the cost is 18 times the square footage that we have. Where C represents the cost of the deck and S equals the number of square feet. So if we have 156 square feet, what will the cost of this be? So we can take $18 times 156. So it would cost us $2,808. Now if we go backwards, the cost is $1,800 equals 18 times the square foot. Using our inverse properties, 1,800 divided by 18 would be 100 square